welcome. Principles of estimation for MIMO or OFDM wireless communication. Okay, in this course, we discuss about the likelihood function and least square cost function for vector parameter estimation. This is A Karthik, Assistant Professor, Department of Electronics and Communication Engineering, Institute of Aeronautical Engineering, Hyderabad. Okay, coming to today's topic is likelihood function. Okay, in the previous session also we discussed likelihood functions and maximum likelihood functions. Okay, coming to what is the difference between the previous sessions and this session means there we have to individually find out the likelihood function of the mean and variance, and also we can find out the maximum likelihood variance and mean. Okay, in this we have to find out the vector parameter. Okay, in this we have to mainly find out the vector parameter that is for the likelihood function. Okay, in the previous session we discussed about the wireless communication system. There we have find out the vector parameter. Vector parameter is nothing but there we having the transmitter vector or receiver vector or channel vector. Okay, that is for the all the communication system. There we discussed the likelihood function estimation. But coming to here, mainly we have to estimate the vector for the motivate of the context of the multi-antenna wireless communication system. This is also we discussed in the previous session. Okay, in this channel estimation, the multiple antenna system and also there we having the downlink. Okay, in the previous session we got to go for the wireless communication system. There we are taking the multi-antenna and they can be find out the some downlink of the transmission system. Okay, next in that previous session we considering the multiple antennas. That means we are taking the multiple inputs and multiple outputs at the mobile station. Okay, coming to here the statistics. Okay, what is the likelihood function we are consider? There we having the some statistic, that means data analysis. Okay, before going to estimate the any function, we have to take in the likelihood function. Statisticals or any data analysis. Then we can move to the estimation of the function. Okay, if for example we have to measure the any goodness of the statistical model. There we having the sample of data given values of the unknown parameter. Okay, why we go for the any estimation of the parameter means we have to know the unknown parameter, then we have to go for the parameters in the statistical model. Okay, coming to any, you have to take in some probability function, that is a probability density function, that is a PDF. Okay, we can find out the a giant PDF in the previous sessions. Coming to here, we are taking the number of samples. For that, also we can find out the probability density function. Okay, it is a function, the parameters only the treating the random variables, fixed the observed values. Okay, then we can having the functions of the parameters. That is also known as some unknown parameters. Okay, coming to in this one, the mainly the likelihood function describes the hypersurface. Okay, here mainly we discuss the hypersurface of the peak. If it is exist, means that is a surface or whatever taken the function that is exist, that it also represents the combination of the model parameter values and also maximize the probability of the drawing sample obtained. That will also we can maximize. Okay, we are go for the combination of the model parameter values and also maximize the probability of the drawing the sample obtained. Okay, this procedure, the procedure for obtaining the arguments, whatever we are taking the procedure. Okay, in the function of the likelihood function, we are taking the some procedure. There we can take in the arguments. Okay, that is the maximum of the likelihood function is known as the maximum likelihood estimation. Okay, first of all we have to take in the likelihood function. We have to maximize the some arguments. Okay, that is in the maximum likelihood function. Then we having the parameters known as the maximum likelihood estimation. Okay, which for computational convenience usually done using the natural algorithm. Okay, this is a natural algorithm we have to take in, and also that is for likelihood, that is nothing but a log likelihood function. Okay, we have the log likelihood function p y bar h. This is the log likelihood function. This is called log likelihood function. Okay, mainly in this one we are taking the some arguments that is called from the likelihood function, that is called maximum likelihood function. Okay, whatever parameter we have to go for the estimation, those we are called the maximum likelihood estimation, which for computational convenience and also that is for using for the natural algorithm of the likelihood. Okay, those values for we are called the log likelihood function. This is a log likelihood function. In the previous sessions also we taken these log likelihood function as an example. Okay, coming to creating a probability of density function, that is a PDF. Okay, coming to any PDF that represents the binomial properties for generating the for getting the heads in single coin toss. Okay, here we taken some example. Okay, that will creating the some probabilities of getting the heads or any uh, tail. So that is in the single coin. Okay, if you go for the any single coin, we have to take in some probabilities there. What is the probability if it is a head or tail? Okay, that is the two possibilities are for that one single coin. That in that example we are taking the some estimation of the likelihood, then we can getting the heads from your data, so you will turn your experiment, then we can go with these possibilities. If you get two heads in a row, okay, if you are uh, place a single coin, then you can two times you get a row, your likelihood function for the probability the coin landing heads up, we look this the graph. Okay, whenever we having the two possibilities, two heads, okay, in a row, then we can having the this graph. Okay, in the likelihood function, this is a graph for the two possibilities at a time. Okay, that is in the coin process. Okay, next one in this, if you are once more get this tail, okay, then we can having the after, first of all we are having the two heads are at a time, after that we get the tail. Okay, then it is goes like this, then we can turn like that, that is the tail. Okay, if we are having the likelihood function, then we having the heads means it go for the peak of the possibilities, that is the probability in the likelihood function, then we can having the again we go for the another probability, that is the tail. Okay, then we can get the say changes like this. Okay, if you are go with the two heads means it is to go for the, this is a probability. Okay, this is a for two heads at a time, two heads in a row. Okay, after that means h and h. Okay, but coming to here we having the h and head and tail, this is a possibility, then we can having the graph like this. Okay, this is the changes for the comparison of these two heads, and this is a one tail in the likelihood function. Okay, what is the functionality of the likelihood also we discussed in the previous session. Okay, in this one we can see the that vector parameter of the likelihood function in the least square cost function. For example, here we can take in the some possibilities of the least square function. Okay, up to now we discussed the likelihood function, then we can move to the least square of the cost function, then we can find out the parameters of the hyperplane. Okay, in this one mainly we find out the hyperplane, which is a fits for a regression data set. Okay, that is a regression data set, it is a common practice for the first from the least square cost function. Okay, least square cost function, if you go with the find out the parameters, that is in the hyperline, and also that is first from the least square function. Okay, that mainly best fits for a regression data set. Okay, coming to for a given set of parameter, for a given set of parameters, w, here I consider is a w is the cost of the function, it computes the total squared error between the associated hyperline and also some data. Okay, this is associated with the both between the hyperline and data, that is we taken the square error. The square error is nothing but a w here we consider. Okay, then giving the good measure of the how will the particular linear models for the data set. Coming to the natural, then the best fitting the hyperline is the parameter maximize the error. The parameter, those who are parameters maximize the error, then we can go for the best fitting for the hyperland. Okay, here this is the least square cost function, here we take in the regression data set. Okay, that is mainly common for the mm, some common practice for the first from the least cost function. Here we take in the where error is a w, here we can associate with the hyperline and the data, and also those data and hyperline giving to the good measure for the how well the particular linear model fits to the data set. Okay, this is in the least square cost function. Okay, coming to the least square regression, the model is a statistical technique. Here we can use the technique is the statistical technique that may use to estimate the linear total cost function. Okay, these least square cost function mainly estimate for the linear total cost function, and also this with the use of the linear total cost function, we can go for the mixed cost based on the past cost data. Then we can go for the based on that. Okay, here the total. The estimation we can taken for the used for the linear total cost data function that is mainly based on that past cost data, that is based on the previous value, that based on the previous value, and also mixed cost. Okay, we can take it individually or mixed cost, that is from the based on the past cost data, that is the previous cost. Then we can measure the linear total cost function. Okay, coming to the function of the least square function, then we can use it to forecast dots costs and to different activity levels. Okay, here we can take in the different activity levels. What are the different activity level means? Then we can consider the all the possibilities. Okay, there we having the what is a previous cost, and the next one is a next future cost also we are taking for this one as a part of the budgeting the process or to support the decision making process. Okay, these we can support the for the making process. Okay, here we can having the function mainly it use we are taking the statistical technique. Okay, in this regression model we are taking the statistical technique, and also it is useful to estimate the linear total cost function for a mixed cost, and also that mixed cost based on the past cost data. Okay, coming to these functions, whatever we are considering the function that we can take in for the that we can use it for to forecast of the 8 different levels. We can consider the 8 different levels we are taking the forecast, and then we can consider as a part of the budgeting process. Okay, or any support to decision making process we are taking these different levels. Okay, coming to same cost function we can take in the some calculation. Okay, here we take in the some calculation is a line of best fit to a set of data pairs. Okay, here we consider pair means we are consider two works are that is mean by that is different levels. Okay, that is series of activity levels and also corresponding to the total cost. Here we can consider the two levels. One is the series of the activity levels. Okay, the series of activity means one by one. Okay, after one activity level means after that and the second activity level, then we can take in the series of actual level, and also we can take in the some corresponding total cost. Okay, whatever activity level, for example here I consider 1 2 3 4, these are the 4 activity levels. That means if you are completion of the one, then we can go with the 2 and next 3 and 4, and corresponding first activity level having the what is the cost. Okay, and total cost, and for that also next is total cost. Okay, then again with the total cost, then we can go with the total cost. Like that we are having these 4 total costs. Okay, then this is a corresponding series of activity. Here we taken the pair data pair, that means the combination of these two. Here we taken the combination of these two. This idea behind the calculation is to minimize the sum of the squares of the vertical distance, that means errors between the data points and also cost function. Okay, mainly in the least square regression function, there we can take in the pair of data. What is a pair of data? That is a series of activities and also the total function of the corresponding series of activity. There we can go over there we can calculation the least square regression, and also we can take in the calculation we have to minimize the sum of the squares of the vertical distance, that is the errors we can take in the minimize to the sum of the squares. And this where we have to take in these sum of the square means that is the data points and a cost function. That is data point means that is a series of data levels, that is a series of activity levels, and also the corresponding cost function. Then we can go with the least square cost function. Okay, in the next further slides we can also derive the equation for the least square cost function. Then you can understand easily. Okay, but this is some calculation of the least square cost function. In the statistical, the lower error means better explanatory power of the regression model. Mainly in this least square function, we go for the regression model. Okay, that is a statistical model also. Then we can go for the regression model. The least square model aims to define the line, minimize the sum of the squared errors. We are trying to determine the line of the closest to all observations at the same time. Okay, what we understand from in this one, you can minimize the whatever values we get from the function, that is in the regression model. We have to minimize the sum of the square errors. We have to take in the sum of the squared errors, and also we have to try in the determine the closest all observation in the same time. This is for only the least square cost function, but in this one we are considering the regression model. Okay, in this one we are considering the regression model, but we are taking the some minimization of the function, that is the sum of the squared errors. Then those function, those are the taking the errors. We are going to take the closest to all observation at the same time. For example, you are considering the one observation model means y equal to h plus v. Okay, this is a one observation model. If you go with the all observation means y1, y2 and so on yn. Okay, there we can go with these different all observation at the same time. We have to take in the all observation average. Here we are taking the all observation average. Like that we can find out the regression model of the calculation. Means mainly we go for the multiple antenna channel. Then we having the estimation. Okay, there we having the estimation means we can go with some function of the any values. Then taken the function model for the multi antenna system also here. Sorry, model for multiple antenna channel estimation. Antenna channel estimation. Okay, in this one mainly we are taking the different vectors. Okay, different vectors means what are the vectors we are having that. For example, you are considering the y equal to h plus v. That means this is an observation parameter. Observation parameter. Okay, in the previous session also you know what is a y, what is a h, what is a v, what is parameter. And h is the channel coefficient parameter. Channel coefficient parameter. And v is the noise parameter. Noise parameter. Okay, here this is for the observation model. We are considering the y equal to h plus v. Here in this one, from this y equal to h plus v, we are having the some vectors. What is the vector? Y bar equal to h bar plus v bar. Okay, from the here we can consider some vector parameters in the any multiple antenna system, and we go for the likelihood function. From that we can go for the likelihood function. Okay, y bar equal to h bar plus v bar. Then you can give here y bar means what is a y bar? Y bar is the observation vector. Observation vector. This is a observation vector. This is a channel coefficient vector. This is a channel coefficient vector. This is a v bar. This is a noise vector. This is a noise vector. Okay, you can understand clearly. Here we can consider the one observation parameter, that is a y equal to h plus v. This is a parameter. Okay, that is a known parameter, unknown parameter. We can go for that parameter. Then we can go for the y bar equal to h bar and plus v bar. Then these are the vectors. Okay, what is a y bar, what is a h bar, what is a v bar? Also we discussed in the previous session. Again, I will see that y bar equal to h bar plus v bar. Then we can write the vector parameters for the y bar and y bar, h bar plus v bar. Then what is the vector parameter for example, here you can consider y bar equal to, we having the y1, y2 and yn. Okay, these are the collection of data, collection of parameters, collection of parameters. These are the collection of parameters for the y bar vector. Okay, next y vector. Next coming to h vector means, okay, here we having the h1, h2 and so on, hn. Okay, this is a collection of parameters of channel, collection of parameters of channel. Okay, collection of parameter of channel. Next coming to next v bar. V bar equal to v1, v2 and so on, vn. These are the noise collection of noise parameter, noise parameters. Okay, here we having the y bar equal to h bar plus v bar. Then y bar equal to collection of parameters, that is a y1, y2 up to yn. That is a collection of all observation parameters. Okay, then we are not go for the any single individual parameter. Y bar is a vector. Vector means nothing but whatever corresponding the values will be there in the that observation. We have to take in the all the observation, that is a y1, y2 up to yn. Coming to h bar means h1, h2 up to hn bar. Okay, HL. This is the collection of the channel coefficient vectors. Coming to V bar means we are having the V1, V2 up to Vn. Those are the collection of the noise parameter. Okay, this is the vector parameters of the that particular any function. Okay, if you are go with the any communication, we have in the transmitter and receiver and channel. Okay, then we can have in the receiver parameter, channel parameter, and transmitter parameter. Here we can consider. Next, we can write the y of 1, y of 2, so on, y of n. Then I can write here equal to x of 1 to xm1 of 1. Okay, next x1 of 2, so on, xm1 of 1. Okay, next, so on, x1 of n, xmn of n. Okay, this is the vectors. Okay, and also consider for the h1, h2 up to hm, and also place v1, v2 up to vm. Okay, here we can take in the this is a n cross 1 observation, n cross 1 observation. Okay, here we can consider this is a pilot symbol, n cross m, pilot symbols are matrix, pilot matrix. Okay, this is a m cross 1. Okay, this is also m cross 1 unknown channel coefficient, unknown channel coefficient. What are those? These are the m cross 1. Okay, m cross 1 noise vector. Okay, you can observe here. Here we having the y1, y2 up to yn, that is a n cross 1 observation matrix. Okay, coming to here we having the pilot symbols, that is a transmitted pilot symbol. Actually, we are having the equation y equal to h x of k plus v of k. Here we having the y of k equal to h into x of k plus v of k. Okay, based on that we can find out for the parameter vectors. Okay, vector parameters we can find out. Here this is a observation vector, that is nothing but received vector. It's nothing but received vector. Those are the y1, y2 up to yn. Coming to here, we having the transmitted vector, that is a x1. In that we are having the different values. That is we can consider for 1, 2, and n. Okay, here we taken the different samples. Okay, that is the transmitted symbols, and also the corresponding whatever transmitted signals symbols, we are having the corresponding values h1, h2 up to hm. And also the with the having the h of x of k, we have to give the some add to nice to the corresponding levels. Then we have taken the v1, v2 up to vn. This is all vectors. Here we have the observation vector and pilot matrix vector, and also nothing but a transmitter vector, and also unknown channel parameter vector, that is coefficient, and also we have the noise vector. Okay, from in this one we can write the vectors y bar equal to x h bar plus v bar. Okay, this is the unknown parameter. This is the parameter vector of the unknown parameter vector. Okay, now we can move to the likelihood function. Okay, up to now we discussed about the different vectors. That is, what are we having the different vectors? We are taking the transmitter vector and receiver vector and channel coefficient vector. Finally, we can add it to the noise vector. Next, we can add it. We are considering the likelihood function. We know that our likelihood function. From the likelihood function, we are taking the different Gaussian noise. So, what is the Gaussian noise? V1, V2 up to so on V of n. Okay, those are called IID. What is the IID? Independent identical distributions. Those are the independent identical distributions. Okay, here we having the independent identical distribution v1, v2 up to v of n, that is a identical distribution. Those are IID. Here we can take in the Gaussian random variables. You can take in the Gaussian random variables. That is there we having the previously also we can find out the what is the likelihood function of There we have taken the Gaussian random variables mean value. Okay, mean value is 0, and also variance sigma square. Variance sigma square. How we can take in the mean value, and this one we are taking the estimation of the v equal to 0, and also estimation of the variance equal to sigma square. These are two we already find out in the previous classes. Now we can consider here likelihood function. There we can take in the mean value 0 and variance of the particular random variables, that is a sigma square. Now we can go for the probability density function. We can go for the probability density function, that is a PDF. Okay, here next we can go for the probability density function, that is a PDF. Okay, that is a PDF. Also we can find out f v of k and v of k equal to 1 by under root 2 pi sigma square e power 1 by 2 sigma square v square of k. Okay, this is also we taken for that giant probability function PDF. Okay, PDF is a probability density function. We also taken for the previous sessions also in the likelihood function. Okay, here the giant. This is next go for the giant probability density, that is a PDF of the. Here we taken the PDF. Then we can go for the giant PDF. So v of 1, v of 2, up to v of n. Here we can consider the individually. Okay, then we can go with that product of the some individual probability density function. Then we can write okay f v of 1 v of 1 into f v of 2 v of 2 so on into f v of n and v of n. Then we can write the substitute all the values here. Then we can what is the value here. Then this substitute the values here. Okay, then I can write f v of 1 means v sorry, here I write this value 1 by 2 pi sigma square e power 1 by 2 pi sigma square into v square of 1 into 1 by under root 2 pi sigma square e power 1 by 2 pi sigma square v square of 2 and plus so on into 1 by 2 pi sigma square under root of 2 pi sigma square e power minus 1 by 2 sigma square v square of n. This is the product of the individual PDF. Then we can write clearly in this all the giant PDF 1 by 2 pi sigma square n by 2 e power minus 1 by 2 pi 2 sigma square. Okay, 2 sigma square summation of k equal to 1 to n v square of k. Summation of k equal to 1 to n. This is the giant PDF of the noise. Okay, giant PDF of noise 1 by 2 pi sigma square n by 2 e power by 1 by 2 pi 2 sigma square summation of k equal to n to v square of a. Here I consider giant probability function of the product of the noise. Okay, for that we can go for the f of f v of 1 and f v of 2 and so on into f v of n and v of n. We consider like this. Then we can having the simplification 1 by 2 pi sigma square e power 1 by 2 pi sigma square v square of 1 into 1 by 2 pi sigma square e power minus 1 by 2 pi 2 sigma square v square of k. V square of 2. Then we have the n product values. Okay, and again we can simplify this for this easy of the computation. We are taking the 1 by 2 pi sigma square whole power of n by 2 e power of minus 1 by 2 sigma square summation of k equal to 1 to n v square of k. This is the giant PDF of the noise symbols of the noise samples. Okay, some symbols are samples. This is a giant PDF, that is a giant probability density function. Okay, next coming to in this one we having the some PDF equal. What is a PDF of equal? In here we go for the v of 1, v of 2 up to v of n. This we have the considering this is the identical values. We are considering the some identical distribution values. There we having the some nice PDF vector. This is a nice vector. Okay, this is a nice vector. We are considering v bar equal to v of 1 and v of n, v v2 of n, v of n. Then we can having that one. Then from in this one we can having the nice vector v bar transpose v bar. Okay, how we can write the v transpose and v bar? Then we can write the v vector. That is a v vector. We know that v of 1, v of 2 up to v of n. Okay, this is for only giant probability density of the probability density function of the nice samples. Okay, up to now this is the different. Now we can consider in the vector. Okay, that purpose I consider that this is the nice vector v equal to v of 1, v of 2 up to v of n. That is a independent integral distribution. Then from in that we can write the v transpose v bar transpose into v bar. Then we can write the v of 1 up to so on v of n. Okay, then also I can write v of 1 v vector. Okay, v of 2 up to v of n. Okay, this is a v transpose v bar v vector transpose and v vector. Okay, then from in this one we can also write sigma equal to k equal to 1 to n v square of k. Okay, we can also write this one. Okay, from this is also v transpose vector and v vector. Okay, this is a v transpose vector and v vector. And also for the simplification in the previous session also we can also write this mod of the v bar vector. Okay, we can also write this one. Okay, just I consider here, don't confuse here. First of all, I taken the what are the parameters from the observation vector y equal to h plus v. That is the only observation parameter. Okay, from the observation parameter we go for the vectors. Okay, from the observation parameters we can go for the vectors. That is a y bar equal to h bar plus v bar. Okay, that is the observation vector and channel coefficient vector and noise vector. Okay, for that we have to find out the some individual vectors. Okay, for that we are having the y bar is those are the collection of the parameters. That is a y1, y2 up to yn. Coming to h bar means h1, h2 up to hn. These are the collection parameter. Next go for the v vector. v1, v2 of vn. That is a collection of the nice parameter vector. Okay, those we are having that different y bar, h bar and v bar. Coming to the next one, we are considering the different samples. Okay, vector we have to write here. That is all the values collection parameter. Okay, we can combine all the parameters here. That is y of 1, y of 2 and y of n equal to, I can write x of 1, x1 of 1 up to so on xm of 1. Next x1 of 2 up to so on xm of 2. Sorry, here xm of 2. Next here we can write the x1 of n to xmn of n. Okay, here I can write xmn of n equal to xmn of n. Okay, like that we can write h1 plus h2 up to so on hm. And plus we can also write some additive nice v1, v2 up to so on vm. Okay, here I can write n cross 1 observation model. Here I can write that is a n by m pilot matrix. That is a transmitter pilot matrix. Okay, here we can having the some unknown channel coefficient. That is m cross 1. Next one here we having the m cross 1 nice vector. This is finally from this y of k equal to hs of h into x of k plus v of k. From in this one I can write the I can consider the likelihood function. In the previous sessions also we discussed clearly what is the variance of the this nice vector, nice, and also what is the mean of that noise. We can also write mean equal to 0, variance equal to sigma square. Okay, coming to probability density function. Here I can write f v of k equal to 1 by under root 2 pi sigma square e power 1 by 2 sigma square v square of k. This is a probability density function. Okay, that is for the v1 noise. Okay, based on the noise we can write this probability density function. Next we can go for the giant probability density function. That means here we can take in the multiplication of the all the parameters. Okay, here we can take in the multiplication of the individual probability density function. Then I can write f v of 1 into f v of 2 into v of 2 into that is for the n samples. Just I substitute these one here. I can write 1 by under root 2 pi sigma square into e power 1 by 2 sigma square v square of 1, because this is this value. Next coming to this one, under root 1 by under root 2 pi sigma square into e power minus 1 by 2 sigma square, that is a v square of 2. Okay, coming to n samples. Okay, for the completion purpose, I taken this one is 1 by 2 sigma 2 pi sigma square whole power of 1 by 2 n by 2 e power of minus 1 by 2 sigma square summation of k equal to 1 to n v square of k. Just I taken the giant PDF of the noise samples, and from in this one I can go for the noise vector. Okay, from in this one we can go for the noise vector, that is a v bar equal to v of 1, v of 2, v of n. Those are the identical matrix. Okay, those are the identical matrix. Then we can go with the v bar transpose v bar. Okay, I can consider the v bar transpose and v bar. Then we can write this is a v bar transpose and this is a v bar. V of 1, v of n, v of 1 to v of n. Here I can write v of 1, v of 2 up to v of n. Then I can write the computational purpose v bar v vector transpose into v vector equal to summation of k equal to 1 to n v square of k. Then I can also simplification purpose I can write mod v vector whole square. From in this one I can write the value of the probability density function f v bar f v bar equal to 1 by root 2 pi sigma square e power 1 by 2 sigma square. I can write v bar mod v bar whole square. This is the value. Okay, from in this one I can simplify this one. Next here we take in the mode of the some observation mode. Mode is y bar equal to x plus h vector plus v bar vector. From in this one I can write v bar equal to what we can write v vector equal to, from in this one v vector equal to y bar minus x h bar. Okay, here I taken the some Gaussian noise. Okay, here the some this is a Gaussian noise. I can write here Gaussian noise this one, that is a v bar equal to y bar minus x into h bar. Okay, here y bar is the some fix of the v bar. Okay, here we taken the some that is the some received function. Okay, here we taken the y bar is a y is a received vector or observation vector, received vector and also observation vector. From in this one we can write the estimation of the y bar equal to x h bar. Okay, I can write this one 1 by 2 pi sigma square e power 1 by 2 1 by 2 sigma square. Okay, here I can write what is a v bar. We know that here what we can write the v bar here. Just I substitute here v bar. Okay, here I substitute v bar. Okay, here I substitute the v bar. Then I can write the same thing here. What is a y bar minus x h bar. Okay, I substitute these value here. This is a likelihood function of the parameter vector of h bar. Okay, here we can write likelihood function of the for parameter vector h, function of for parameter vector h bar. Okay, here and also from in this one we can write the likelihood function. From in this one we can write the likelihood function probability of the y bar into h, that is a likelihood function. Likelihood function likelihood function. Here we having the in the likelihood function we can having the from the p into y bar h equal to, here I can write this is observation. Okay, in the likelihood function this is observation and this one is a parameter vector. Okay, parameter vector. Okay, here we can go for the log likelihood function. up to because why we go for the log likelihood function, that is in we discussed in the first slide. We can maximize the natural logarithm, then we can go for the maximum likelihood function, then we can go for applying the log likelihood function. Log likelihood function, we can apply the log likelihood function, then we can write the natural log y bar into h bar equal to natural logarithm of p y bar into h bar. Okay, then we can write here, this one is a minus n by 2, this is from previous sessions. Natural logarithm of 2 by sigma square minus 1 by 2 sigma square, and also we can write y bar in minus x h bar whole square, that is a mod. Okay, from in this one we can write the maximize the this value y bar into y bar and h bar. Okay, we can maximize this value, then we can write the, this is for the maximum value. Coming to this minimum value, minimum equal to we can write mod y bar minus x h bar whole square, this is the minimum. Okay, here this is the maximum likelihood estimation of the h vector. Here this is the maximum likelihood function, maximum likelihood estimation of the h vector, and also it can forward by the same maximally for the this value. Okay, this one value we can maximize to the maximum likelihood function. Okay, from the likelihood function, here we consider the likelihood function. From the likelihood function we have to take the function values to a maximum, then we can go for the maximum likelihood function. This is we can go with the minimum value is the mod y bar minus x h bar h bar square. Then we can go for the maximization, then we can write this value into in the h vector y bar minus x h bar h whole square, this is in the maximally by taken in the maximum likelihood function. Then here the maximum likelihood estimation, it's the least square normal. Here we can take in the least square. Okay, here we can take in the least square, here we can take in the least square cost function, here we can take in the least square cost function of the vector parameter. Okay, for any problem here considering that this one is the least square cost function. Okay, in the first of all we have go for the maximum likelihood, then we can maximize the likelihood function, then we can write the least square cost function, then we can write the mod y bar minus x h bar whole square. Okay, then we can write this function in the all the parameters. Okay, here we can take in the probability density function, that is a f value, f is the f v of k, and go for the values is the 1 by under root 2 pi sigma square e power minus 1 by 2 sigma square into v square of k. Then we can go for the giant probability density function. There we having the individual probability density function v of 1 in the noise, v of 1, v of 2, up to so on, v of n. Then we can take in the multiplying the individual parameters. Okay, we are considering the individual parameters, then we can write the f v of 1 into v of 1 plus into multiplication, we are taking the individual parameters, then we can write f v of 2 v of 2 into f v of n and v of n. Then I substitute the probability density function of the values in this one. Okay, that is 1 by 2 under root 2 pi sigma square e power 1 by 2 sigma square v square of 1, that multiply to the 1 by 2 sigma 2 pi sigma square e power minus 1 by 2 sigma square v square of 2, that is for n sample values. Okay, from in this one for the computational purpose I can write 1 by 2 pi sigma square whole power of n by 2 e power 1 by 2 sigma square summation of k equal to 1 to n v square of k. Okay, this is the joint probability density function of the noise samples. Okay, those are the joint probability density of the all the noise samples. Okay, this is for the only probability density function. This is a PDF, that is a probability density function. Okay, from in that we can consider the Gaussian noise samples. Those are the v of 1, v of 2 and v of n. Okay, this is also called independent identical distribution. Okay, for that I can consider the multiplication of the all the samples, then we can write the all the samples means we that we can write here 1 by 2 pi sigma square whole power n by 2 e power 1 by 2 sigma square summation of k equal to 1 to n v square of k. This is a giant probability density function of the noise samples. Okay, from in that I can consider the noise vector v bar. Okay, here we can consider v bar. We know it from the previous session also what is the v bar values. Okay, from in that we can consider v bar transpose into v bar. Then I can write this is a matrix. This is a v bar transpose and this is a v bar. Okay, for the computational purpose, I can simplify this one. Summation of k equal to 1 to n v square of k. Then I can write this is the final mod v bar whole square. Okay, v bar square. Okay, this is the function of the noise. Okay, from in this one, I can simplify the f v bar whole and v bar. Okay, so that is a suffix. I can consider here 1 by 2 pi sigma square e power 1 by 2 sigma square, then they can write v bar square. Okay, that is one mode of the y bar equal to h plus x into h bar plus v bar. That is we knowing from the previous session also. Okay, then we can consider some Gaussian noise, that v bar equal to y bar minus x h bar. Then I can consider the received vector. From that received vector, I can consider this is a value equal to, I substitute this value, that is whatever we have find out the v bar value, I substitute here, that is 1 by 2 pi sigma square e power 1 by 2 sigma square y bar minus x h bar whole square. This is a likelihood function for the parameter vector. Okay, and also we can consider the likelihood function in the probability, that is a y bar and h bar vector, that is in the likelihood function. From in this one I can consider the log likelihood function. Okay, they'll be having the likelihood function, then we can go for the log likelihood function. Okay, log likelihood function means that is individually we taken the natural logarithm, that is a natural logarithm equal to p into y bar into h. Then I can also simplify the minus n by 2 natural logarithm 2 pi sigma square minus 1 by 2 sigma square. That is a value. This is a value I can substitute here. Okay, from in this one we can go for the maximum value and minimum value. From in this one I can consider the maximum value and also minimum value. Then we have in the maximum likelihood function of the h bar. Okay, here I consider this is the least square cost function. Okay, here the mention likelihood function and also least square function for the vector parameter. Okay, from in this one I can consider the likelihood function and then go for the likelihood function. Okay, from in this one we finally find out the least square cost function. Okay, this is the least square cost function. What is the least square cost function? Means mod y bar minus x h bar whole square. That is the vector parameters. Okay, those are comes under the vector parameters. There we can consider the all the values. Okay, for example, if you go for the y bar means we can consider the all the corresponding vectors of the transmitted symbols. Okay, you can consider the all the transmitted vector samples. Then again we can go with the corresponding noise samples also. Okay, with the transmitter and receiver we have the some channel coefficient vector also. That's why we can find out the all the parameters. We can calculate the all the parameters. Then we can go for the observation parameter, that is a y bar. Okay, that is a y bar minus x h bar whole square. This is the least square cost function. Okay, in the next class we can go for the another vector parameterization. Okay, then we can also find out the mean values and also variance values of the wireless communication system. Okay, we can discuss in the next session. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.